Hey everyone, my name is Elie Schoppik. I'm the head of technical training here at Anthropic. A little bit about me, I've been in the education and engineering space for the past 12 years. I recently ran my own coding bootcamp in the Bay Area and previously was doing engineering, working at a bunch of edtech startups, also at a fintech company doing quite a bit in the engineering space. So kind of made my way to teaching AI machine learning, and I get to do that a lot at Anthropic, which you're all very familiar with who Anthropic is. I'll give you a very quick overview, and we'll talk about what we're going to be doing. I also know that you've been in quite a few sessions, so we're going to make sure we take a break at some point in the middle just so you can stretch and get up or have some coffee or some water or something. So I'll do my absolute best to make sure that this is not just a ton of time of me talking at you. At the same time, welcome any questions. I have the chat open, so feel free to just throw some questions in the chat there, or for those of you live that just want to kind of come off mute and ask a question, raise your hand, feel free to do that. I want to make this as interactive and engaging as possible because I know you've all had a lot of instruction today, so I'll do my best to kind of follow up strong. So without further ado, let's get into it. What are we going to do here? We're going to have a quick overview of Anthropic. We're going to talk about how LLMs like Claude are made. So we're actually going to dive a little bit deeper into more of the fundamental machine learning and data science concepts that are not necessarily going to make you a phenomenal engineer, but are going to make you a lot more aware of what's actually happening under the hood here. And when you hear terms like reinforcement learning from human feedback or supervised learning or fine tuning or so on, you actually know what that means in the context of how these things are made. So they feel a lot like black boxes, and I want to do my best to pull apart what we can and what we even understand of these black boxes. We'll then shift gears into prompt engineering, which is absolutely a science and an art. We'll talk about some of the tools that we have at your disposal to excel at prompt engineering, how to iterate on your prompts, and how we see many of our customers do that in the real world. We'll talk a little bit about tool use. So if you're familiar with the idea of function calling from other LLMs, where you've seen tool use in action, I know you've had some exposure to working with Claude and a little bit around the ecosystem. Want to make sure you're feeling good about those ideas. We'll talk a little bit about RAG architecture and tips and interesting things that are coming up in that space. I know, again, it's going to be a slight review for some of you, but I really want to lean into answering questions that you have and definitely giving you some insight and stories from what we're seeing on our end. I want to talk a little bit about the idea of fine-tuning and when you might want to consider something like fine-tuning. Many times fine-tuning seems like the perfect answer to everything, but many times it's actually not. So I'll do my best to help kind of figure out that piece. And then finally, even though this is number 7, I welcome this at any point throughout the entire talk. So any questions that you have, feel free to throw those in chat, raise your hand. I want to make this, again, as engaging and interactive as we possibly can. So we're going to start with a quick overview of Anthropic. We are a frontier research lab, and we develop highly intelligent models as well as introduce some of the most groundbreaking research in this space. So our goal is to develop artificial intelligence that is safe, that is harmless, that is helpful, and that is honest. And over a relatively short period of time, we've been able to do some pretty incredible work. And that culminates with the release of our most recent model, Claude 3.5 Sonnet, that has quite a few capabilities from coding to many other real world use cases that I'll talk about in a little bit. But one of the things that we really pride ourselves on is prioritizing AI safety at the frontier. So thinking a tremendous amount about the kinds of safety concerns, being responsible in the way that we think about security, and being really cautious as we start developing more and more intelligent models that have much higher security concerns. All right, awesome. Note taker is on. Just to give you a little bit of an idea in terms of a benchmark, again, what you're looking at here is how Claude 3.5 Sonnet compares to previous Claude models as well as other models in the space. Again, I'm a firm believer that as we start building larger and larger applications using LLMs, there's not going to be one model that fits every single use case. So depending on what the concerns are that you have, that might be, I need something that's really intelligent. I need something that's really fast. I need something that's really cost effective. These are all things that you have to balance when you pick the model that you want to work with. So while Claude 3.5 Sonnet does excel at many things, there are many other models that do lots of other things well. So we do quite well on many text-based evaluations as well as multimodal or visual type of assessments as well. So something we've been really proud of is our ability to innovate quickly and catch up quite a bit with players in the space. So the model we're going to be playing around with is Claude 3.5 Sonnet. That is our latest model, and we're really excited to show you that in action. Another really important piece that I'm going to talk about when we talk about how models are developed is how we think a lot about AI safety. Because when these models are trained in the entire training process, they're not inherently safe. You could ask the model after it's trained on a corpus or tremendous amount of internet data how to do some pretty dangerous things, how to do some pretty harmful things, how to lie to people and, perform all sorts of really horrible operations you could imagine. So there is a very, very thorough and rigorous process that we go through to train these models to be honest, helpful, and harmless. And one of the real important innovations that we made in this space is the advent of something called constitutional AI. And constitutional AI is where we take a model and we train a separate model on principles that we as a society have agreed upon are valuable to our society and beneficial to human lives. These could be things like the UN Declaration of Human Rights, terms of service agreements, constitutions that we've incorporated as a society that help us kind of build technology that is best for everyone. And we take this little model and we train it just on those particular pieces. And then we use that model to train other models on how to be safe and honest and helpful and harmless. We still absolutely have human feedback in this process, but by creating this smaller model, we can actually train much more efficiently to be honest, helpful, and harmless. I'll talk about that training process pretty soon. So let's first dive in with our topic. We're going to start talking about how LLMs or large language models like Claude are made. The goals here, again, we're going to talk about the idea of model architecture. We're going to talk about what pre-training is. We're going to understand how these models actually work. We're going to explore fine-tuning, reinforcement learning from human feedback. And then again, we're going to answer all the questions. So as you have questions with anything in this process, there's quite a bit of information here that is sensitive and confidential that I just will not be able to share. And I'll be glad to tell you if that is the answer to your question. But I'll be happy to talk at a high level about how models like Claude are trained. All of these models are trained in slightly different ways and slightly different patterns with slightly different techniques. But at the end of the day, the major steps are still the same for all of these models, whether they're Claude or other models in this space. And it really starts with a simple diagram like this. The first thing that we do is we decide on the architecture of our model. When we talk about the architecture, we're talking about the underlying hardware that we're going to use. So you might have heard of a company called NVIDIA that makes a very, very powerful piece of hardware called a GPU. There are also competitors to GPU. Google has their own hardware. Other companies have their own hardware. This is one of the decisions that you make very early on in the process. You choose what kind of hardware you are going to use to perform lots and lots and lots and lots and lots of mathematical operations in parallel. The next thing we think about with our architecture is how we want our network to be designed. And I'm going to talk about that piece when we talk a little bit about neural networks. That's the very first thing we have to pick. These decisions are pretty concrete. Once you think about the hardware that you're going to use, it's not very easy to go and Command Z or undo and say, oh, let's actually just flip this to something new. So these decisions kind of go in order of how serious, how permanent essentially they are for the model that you're making. So we're going to start by talking about architecture. We're going to move on to the idea of pre-training. And this is where you might hear people talk about the idea of we take all the data that's available, all the data on the internet, all the data that we get from all kinds of places, and we try to get the model to predict the next word. Something like that, but we'll dive in a little bit more. This is the idea of unsupervised or self-supervised learning that we'll talk about with pre-training. This usually takes a couple months. This is a pretty long process. This is incredibly computationally intensive and very expensive and takes a lot of energy and money and time. The last step that we do is a process called fine-tuning, and that's a little bit shorter, and that's where we kind of steer the model a bit to behave the way we want to and the way that we can converse with it or whatever else we want to do. So we'll talk about those three phases of this process. What do we mean by any of this again? When we talk about architecture, pre-training, and so on. Well, to try to explain this, I actually asked Claude to see if it could give me a high-level idea of how we can think about these models and how they work. And the way that I want you to think about these models is really, we need three things. We need some kind of way of processing things. We need some kind of way of learning. And we need some kind of objective for what we want to learn. Essentially, we need a brain. We need some way for this brain to learn. And then we have to give this brain something to learn. And that is at a very, very high level how I want you to think of these large language models. And when we talk about things like neural networks and so on, we're actually trying to mimic neurons in the brain and the ways that they work. So that's why you're going to hear this term brain used quite a bit. We're going to give this brain a way to learn, the same way that we as humans sit in the class and we are given a way to learn. And then we're going to give it something to learn. In this case, when we talk about a way to learn, that's going to be the architecture. When we talk about something to learn, that is going to be the pre-training process, where we're going to find a lot of data. We're going to give this model something to learn. Again, just want to pause, see if there are any questions as we go through this. So feel free, again, raise your hand, throw it in the chat. Happy to have a conversation about any of this stuff. Yeah, Lucas, please. And if I'm pronouncing anything, please yell at me.
Thank you. So I really like that there's a huge focus on AI safety, and I wanted to know if you think there are any measures that the developers have to take in order to use the APIs as well.
Yeah, definitely. So it's a really interesting question, because I think that we put so much time and effort into the safety measures that it actually sometimes is slightly frustrating for developers. And what I mean by that is sometimes you as a developer, you want to try to ask something that is slightly controversial, or maybe you're doing something where you feel like it's the right thing, but the model is telling you no. That's actually where it's a little bit more challenging for developers. And that's where you have to leverage prompt engineering, or also just acknowledge that maybe this model is not the right use case for what you're trying to do. Certain models have certain safety measures in place, especially as they get more powerful. But there isn't much on the developer front or the user of the API in terms of things that you need to think about for safety with the model. However, when you are generating prompts, when you are writing system prompts and so on, it is possible that these models may have security vulnerabilities where system prompts are leaked. In fact, at Anthropic, we publicly just list our system prompt on our website, because there's nothing that we're trying to hide in there, and we know that it's going to be a matter of time until people can somehow figure out a way to prompt to get it out of the mix. You have to be careful as the user of any large language model. If what you are posting in your system prompt is sensitive, that is always a bad idea, because somebody will most likely get a chance to get access to that. There's nothing inherently super secure about the system prompt. You can do your best to try to avoid it. And most of the time you can get away with it, but it's one of those things where you just want to be really, really cognizant. So in terms of the underlying safety, you want to be cautious about making sure that the information you are using for your entire prompting process does not contain sensitive information. So that's where you want to think about security stuff.
Perfect, thank you.
Yeah, absolutely. Any other questions as we go through? All right, awesome. Architecture. I want to start with a very simple case study. Some of you may have seen this before. This is a very, very old data set called the MNIST, or MNIST data set. I do not remember for the life of me what that acronym stands for, but this basically was one of the very first neural networks that was trained to actually do some really interesting things. And in this case, it's actually all about recognizing digits. So the MNIST data set is a very large data set of lots of handwritten numbers between 0 through 9. And what we were able to do, and this was years and years and years ago, is train a neural network, train some kind of machine learning model to recognize a digit, a brand new handwritten digit, and then output with a certain probability what the likelihood is of that being the particular number. You can see here sometimes it's relatively easy. If there's a straight up circle that's pretty clear, that's usually going to be a 0. But as you start seeing things kind of blur together, this, to us could look like a 4, but maybe it's a 7 with some scratching, or maybe it's closer to a 1 or so on. So some of these examples are a little bit harder to potentially decipher. And what we're going to do is we are going to build a model that takes in some kind of number and figures out what it actually is. This is between 0 and 9. The way that we do this is we develop what's called an architecture. Again, you do not need to worry about what is a CNN and what is kernel padding and pooling and so on. But all that we do here is we take some kind of input and we figure out at the smallest possible level, at the smallest possible pixel level, what it looks like. And we take each one of those pixels and we treat it as a node in our network. When we talk about the architecture of our model, this is what we're talking about. How many layers? How many nodes? What is the connection between those nodes? That part is the architecture. This is where there's a decent amount of math and a decent amount of machine learning and so on that goes into the underlying architecture, but you yourself do not need to be extremely aware of all the processes that go through. But whenever you see a diagram like this, when people talk about a neural network, that is the architecture. There are lots of variables that go in the architecture. How many nodes do I have? How many layers do I have from the beginning to the end? This right here is the architecture. What actually happens under the hood with this architecture? We take some input, we do a bunch of math. We do a bunch of math, 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 and we output some kind of number. When we talk about things like a bunch of math, it's actually not incredibly sophisticated mathematics. If you've taken a calculus class or two, this is matrix multiplication. If you've studied some linear algebra, that's what we're doing here. If you have not come across any of that at all, that's totally fine. You do not need to worry about the underlying math that's happening here. All I want to show you is that when people talk about architecture and so on, or people talk about training models and building models from scratch, this is the stuff they think about at first, the underlying architecture that I have here. And this is the idea of model architecture. The next piece that I mentioned is that we do a bunch of multiplication. We take one little pixel here and we multiply it over and over and over and over and over again. And we figure out that somehow this pixel right here is part of a larger number 2. The way that we do that is in the process of all of our multiplication, all of our matrix math, there are specific numbers that get changed and multiplied together to produce the right output. Those smart numbers are often called model weights. So if you hear about things like a llama 7b or llama 405b or so on, that basically is how many smart numbers, how many weights does that particular model have? We're going to talk about the weights when we talk about things like pre-training and fine-tuning. Right now, we're not concerned with making these numbers smart or accurate. We're just concerned with how do we take our data, how do we take our input, how do we figure out the output? How many layers do we have? How many nodes do we have? And in this case, here's what they did with the MNIST study. They had some kind of input, and they broke it up. There's an initial layer, and there's an output layer. And there's a bunch of math that happens between each of these nodes. A little bit of math from here to here, from here to here, a little bit of math from here to here, and here to here. The way that this model is trained, the way that it essentially is able to figure out that after going through this many times, the answer is 2, is through the pre-training process that I'll talk about in a little bit. So I don't want you to worry too much about how we go from 2 to 2. I just want you to know that when we talk about architecture, this is what we're talking about. The weights, that stuff, the magic numbers, that comes later. In fact, I'll be happy to share these slides here, but you can actually go ahead and play around with your own little networks. Just to give you an idea of what this actually looks like, this is a problem here where I want to figure out all the blue and I want to figure out all the orange. And I want to figure out what kind of network I need and how that data is going to change. So I'm actually going to run the training of this, and we're going to see that over time, it gets a lot better. All of these knobs and dials, I can add more layers, I can add more neurons. This is the architecture. How many layers, how many neurons does this get me to where I want faster? Oh, in fact, this architecture is actually a lot worse. This is not doing much better. So when we talk about things like model architecture, these are the knobs and dials that we're talking about. This is what machine learning experts do. This is not at the software engineering level. This is not even at the AI engineering level. This is really at the true data science and machine learning level. But I want to make sure that you have an idea of how these things are actually created, because the more that you can kind of pull apart the layers, for lack of a better word, the more you can actually understand when people talk about the neural networks and parameters and weights and so on. This is what we're thinking about. So you can play around with yourself, with those networks yourself. If you want to learn more about these ideas, there is plenty of excellent documentation about what all these parameters mean, learning weights and activation, regularization, and so on. But for now, think of this as just a bunch of knobs that you can tweak to get to what you want to get to. In our case, the architecture that we use is something called a transformer. You might have come across this term, transformer architecture. A transformer architecture is just a different architecture than we previously used for building neural networks. And transformers themselves allow us to operate on lots and lots of things in parallel. One of the big, really nice advantages of transformers is the ability to operate on lots of numbers in parallel. That's why we use this architecture. The way that these large language models work is through a process called sequential prediction. What that basically means, in a nutshell, all that a large language model is it's a really good next word guesser. And what I mean by that is, when you give the model something like the quick brown fox jumped over the lazy The model's job is just to figure out what comes next. What is the single word or block of code or number or character or pixel that comes next? That's all that this process is. This is a very fancy term called sampling, which is simply pick the next possible piece of information that should occur in this text. And the way that we do that is by taking these words and bringing it down to numbers. Remember, we got to get to numbers so that we can do lots of math. This process of taking each of these words or portions of words and turning them into numbers is called tokenization. You might hear the term tokenizing or a token. What that basically means is for each of these words or portions of these words, we have a particular number, a particular lookup for it. This is essentially like a dictionary of sort. The maps to this, quick maps to this, fox maps to this. We run it through a bunch of really smart numbers and math. And what we get at the very end is a bunch of probabilities. And those probabilities correspond to a particular token, a particular word. And that's how we figure out, with the most likely probability, what the next word is. It's really all that these things do. They are simply just next word predictors. But they're really, they are in fact surprisingly almost magically good at it. That is what is so kind of groundbreaking about this technology. Not only are they really good at predicting the next word, but they can also be relatively creative in how they think about the next word. So at the end of the day, this is how we think about our architecture. We're using a transformer architecture, leverages hardware that can be run in parallel to do lots of computations, because we're doing tons and tons and tons of math to figure out all these words and what comes next. To get to many words, to figure out the next word in the sentence, we go through this process called sampling. This is taken from a really wonderful tutorial by 3 Blue, 1 Brown that I recommend if you want to dig more into this architecture you can look into. But we basically take the first word and we figure out with the biggest probability what the next word's going to be. In this case, I'm using the term word and token synonymously, but in larger applications, tokens are usually portions of words or spaces and characters and so on. Different large language models do tokenization differently. And we figure out behold. What comes after behold? A comma. After the comma, behold wild. Behold a wild pie. Behold a wild pie creature. And we go with this sentence and the next word and the next word and the next word and the next word. In the transformer architecture, there is a very powerful mechanism called attention. And this comes from a paper called Attention is All You Need. That was kind of the thing that kickstarted this entire phenomena in large language models. And in the transformer architecture, the idea of attention is that we can not only pay attention to the next word, but we can think a lot about what the next word's going to be based on all the things that we have seen up until that point. So when we type in, behold, a wild pie creature foraging in the native habitat of mathematical formulas and computer code with its infinite digits and, the next word is not just what comes after and. The next word is what comes after and also paying attention to everything that came before it. That's what makes these so useful. Because if the only thing we looked at was the previous word, we'd come up with gibberish. We wouldn't be able to come up with novels and stories, and we wouldn't have a large language model tell us something like, and the murderer was X, or the winner of the game was blank, because you need all that context before. You need to pay attention to everything that came before. So when you hear about things like attention, attention head, multi-head attention, and so on, it's all part of the architecture that we're using. Again, that fancy word of sampling, we predict probabilities for the next token, we pick a token based on those probabilities, and then we repeat and repeat and repeat and repeat and repeat and repeat. And that's really it. That's how these things work. Yeah, Lucas, please.
Just a quick question. So how does attention converts to context, or like, yeah?
It's basically the same kind of idea. So the cumulative attention that you have is passed forward in the entire network in the transformer architecture. The term context really refers to how many tokens you can have in the entire conversation or entire one conversation. So context itself, or context window, usually means how many input tokens and how many output tokens. What is the sum of those two numbers? And once I get past that point, I just can't fit any more in memory. So think of context window the same way you think of memory in some kind of software or even hardware application. There's only so much that you can fit into memory at one point in time. think of context window the same way. But in the case of the transformer architecture and our tokenization process, when you ask the model something, you're feeding it a bunch of input tokens. We then figure out those tokens and the weight and how many tokens are calculated, and then the model gives you back an output. With input tokens, it's you put into the model what you put in. With output tokens, you can tell the model, hey, I only want a certain number of output tokens, or I want you to stop at a certain point. Those are all settings you can put on the model. The context usually refers to kind of the memory, which is really just the sum of the input and output tokens for an entire conversation.
Okay.
You might have also heard this term temperature, or you've seen this setting of temperature that you can set. What does temperature really do at the end of the day? Temperature just adjusts the probabilities and which ones you are likely going to select. So if I have some kind of piece of text like the quick brown, by default, if the temperature is at a normal setting, we're going to see a probability distribution that looks like this. And we're probably going to go with Fox. Again, we're never guaranteed to go with Fox, but 60% of the time we are going to go with it. So when you think of these probabilities, I don't want you to think of, oh, it just always picks the highest one. Remember, these models are non-deterministic. If I ask the question, what is, the most beautiful color in the world, give me one answer, I'm going to get a very different answer each time that I do that over and over again, because it's going to pick a token. It's not always going to pick a token with the highest probability. It's just like a game of chance. 20% chance it's dog, 20% chance it's cat, 60% chance it's fox. If you adjust the temperature, what you are basically doing is you are changing the distribution of those probabilities. If you change the temperature to something very, very, very low, we're basically going to say, all right, we're probably going to go with fox. If we make the temperature very high, we are basically making the probabilities a little bit more flat. And that way you might pick something that you might not normally choose. People like to say changing the temperature makes the model more creative. Maybe more creative in the sense that it's just going to pick stuff that you wouldn't expect it to pick or that it might not normally pick. So that could lead to more creative output, but not necessarily. This is all the idea of architecture. Architecture, again, what's the hardware that you're using? What is the underlying architecture? You're using transformers. That is most commonly the architecture that we use at larger scale with these models. In those transformers, how many layers? What does the connection look like? What's the math that's happening behind the scenes? That's all part of the underlying architecture. Once we figured out what the architecture is going to be, we're using GPUs from NVIDIA. We're going to use this many GPUs. We're going to have this much, this many nodes and this many layers in our network. Now we have to actually go and train this thing. And the first part of the process for building an LLM is called the pre-training process. We talked a bit about how the model does math with smart numbers, billions or trillions of numbers. How do we figure out what those numbers are? Well, we go through a process called pre-training. We get a bunch of data. This is where people like to say, you get data from the internet. Yes, you can get data from many different sources. It is extremely proprietary for each of these companies where they get their data from, but we get a whole bunch of data. And what we basically do is we play a pretty kind of silly guessing game with this model. We give the model a bunch of text and we give it an objective. And the objective basically is figure out the next word. And we're going to go ahead and we're going to have the model do this over and over and over and over and over again with a tremendous amount of text, lots of different contexts. The goal of this process is not to build a model that can figure out from any Wikipedia article what the next character is going to be, what the next word's going to be. If a word is missing, it knows exactly what to fill in. The goal of this process is to get the model to understand behaviors in language, in the case of multi-languages, so many different languages. So the goal of the pre-training process is not to make a model that figures out if you give it any text on the internet what the next word is, but instead, if you give it some arbitrary text, can it start to figure out the context of what that text is? Can it start to figure out based on other things that it's seen, what is most likely going to come next, what it's mostly trying to refer to? And that process is the pre-training process. Have the model read the data and define an objective. So we might have something like Mount Royal is the mountain in the city of, and we expect that the answer is Montreal, but the model, let's say, outputs these potential options. When the model does something wrong in the pre-training process, when the model does something incorrect, we adjust the weights. The way that we adjust the weights is we work our way backwards from the answer, and we try to figure out where in the process did we go wrong, and we try to minimize the error or the likelihood of that error happening again. We work our way backwards to the beginning of the network, This is a process called backpropagation. You might also hear the term gradient descent. It's basically a very fancy way of saying, fix the mistake I made by figuring out where you made the biggest mistake, and then try it again and see if you did better. And if you did better, great. Stick with those weights, stick with those adjustments in the numbers that you made. But this process is simply take some data, run it through, figure out what's next. Did you get something right? Great. That means that the weights that we have for this particular example, we're doing a pretty good job. You put something in, you get something that is completely wrong. Okay, let's work our way backwards and see where we made a mistake. Let's figure out where the greatest error happens to be. If you go back to your calculus days, this is figuring out derivatives and the greatest rate of change in your entire function for figuring out what the correct answer is. And we just do that over and over and over and over again. As you can imagine, to get this to work well, it takes lots of time, lots of compute. And one of the things that's been incredibly surprising about this process is the more time and money and compute that you throw at this, the better that it does by leaps and bounds. So that's really the difference between something like GPT-2 or GPT-3 and so on, even things like GPT-4 or future models that are just better and better and better. So we go ahead and we say, you should have put in Montreal. We're going to go ahead and nudge those weights in a direction that would have likely led to Montreal. We're not going to go too crazy. We'll make some small adjustments and we'll do it again, do it again, do it again, and see if we're getting back on the right track. This is basically the idea of gradient descent. You'll also hear the term backpropagation. Again, not things that you need to know of from a mathematical level, but it's really valuable to know this because when you work with a large language model and you ask it something and you get the wrong answer, it's not because the very last thing that you put, the thing after it was wrong. It's because somewhere in the process of generating the answer, things went wrong. And that's a really important philosophy for debugging these kinds of applications. When you're not getting the thing that you want, it's not because the very last word didn't know what came next. It's because something in your entire process of prediction went wrong. Like we mentioned, the pre-training process takes tens of thousands of compute accelerators, GPUs or TPUs, which are made by Google, and months of time, trained on huge amounts of data. And what you get back is not actually the ChatGPT or Claude that you are familiar with. You get back what's called a document completer. We'll talk about that document completer in a second. To recap so far, take lots of data, let the model dream, play a bunch of guessing games, let it fix its mistakes. The architecture we use is called a transformer and uses hardware like GPUs to do things in parallel. And when this is done, we get what's called a base model. In your day-to-day coding or use of large language models, you will never use a base model because there's one last process. It's called pre-training and not just training because here's what you get back. You get back what's called a base model. If you're curious to play with the base model, you can go on Hugging Face and you can download base models. But what they basically give you are gigantic auto-completions. So if you ask a question like, who is the president of the United States, you're going to get something that looks like this. The president is the head of the executive government. They're responsible. The judicial branch is responsible. The legislative branch. I didn't ask any of this stuff. You're giving me facts that are accurate, which is great. You're giving me something that's kind of on the right track, but I really got to steer your behavior into something that I can actually have a conversation with. And that is the purpose of the last process when training models. It's called fine-tuning. Fine-tuning is the process of taking this behavior and getting it into something that can complete sentences, knows that its name is Claude, knows how to turn your output into JSON, knows how to answer questions, knows how to handle things safely. In the fine-tuning process, there are a couple things we need to do. We need to be able to have the model produce the behavior that we want. So when I ask a model who is the president of the United States in 1888, I need to make sure that at some point in time, the model has done something like that before. I need to have proof that the model can do it before I ship that out everywhere. The next thing I need to do is I need to reward the model for producing that behavior. I need to give it some kind of number, score, positive result to produce that behavior. The analogy that I'm going to bring here is actually like training a dog. I want you to think of the pre-trained model that we get. This is going to sound a little bit silly, like a wild animal. It is a complete wild animal. It's a dog. It's not vicious. It's not going to attack you, but it's just a dog that's been in the wild that has absolutely no idea how to do anything. At the same time, you need to learn how to train this dog. So I want you to take someone like me who has never had a dog, who has no idea how to train a dog. And we're going to bring Elie into the equation, and we're going to bring our wild animal into the equation. And the first thing we need to do is we need to teach Elie how to train a dog. So we're going to go ahead and we're going to go through some process. We're going to build another model whose job is to learn how to train a dog. We're then, once we have Elie, the dog trainer, all figured out, we're going to go ahead and use this Elie dog trainer to train the actual wild animal. What does that look like? What are the words you're going to hear? You're going to get a process called supervised learning. Supervised learning is the very first thing that we're going to do. You're also going to hear this called supervised fine-tuning. This is basically where we give it some input and we give it some expected output. I want to just show you what good behavior looks like. That's it. I want to show you what a conversation looks like. I want to show you what JSON looks like. The next thing that we do is we train a separate model, often called a PM. This is called a preference model. In the example before, Elie Schoppik, the dog trainer, that's the preference model. The preference model is another model that we make that is trained on how to train a wild dog, in this case, the model that we have, the base model. The way that we do that process is what is called reinforcement learning. So what happens here is we train a separate model called a preference model. The preference model gets good at figuring out what is a good answer and what is a bad answer. In fact, instead of completing the next word or token, it actually just takes in 2 inputs and figures out which one is better. That's it. Just takes in A and B and figures out it's A or it's B. We use that in a process called reinforcement learning. And reinforcement learning is where we take our model, take our base model, the glorified text completer, and we put it in a bunch of environments. These environments could be a conversation with a human. These environments could be reading a textbook and answering questions. These environments could be responding to customer questions based on some chat. And what we basically do is we use the preference model to figure out, as the model is answering questions, whether it's done a good job or not. If it's done a good job, we reward it. We tell it, keep doing that. That's good. If it's done a bad job, we penalize it. So this entire process is what makes fine-tuning. The first thing we do is this supervised learning where we say, okay, base model, you've got a whole bunch of data that you're just outputting. I want to show you some good examples. When I give you an input, here's what I want the output to be. When I ask for JSON, here's what it looks like. When I ask you what your name is, you say Claude. That gets us in the right direction. But if we want to make this model really do interesting things, think on its own, think about different contexts, be aware of many different environments, that's where this second piece comes in. Supervised learning, the pre-trained LLM is fine-tuned on data sets. What do we mean by data sets? Data to encourage specific behavior, high-quality conversations. When we talk about supervised learning, the data that we use in supervised learning is minuscule compared to pre-training. Pre-training, we are using basically the internet. Supervised learning, we're being really intentional, a curated data set, we're being meticulous about what we do. For example, if you see this kind of response, or you see this kind of prompt, generate this kind of response. These could be generated by humans, these could be generated by models, but this is how we teach the model to do things like, when I ask you a question and I say respond with JSON, show me this. When I ask you a question, all I want is this answer right here. That is the idea of supervised learning. So you're going to hear things like SL or SFT, supervised learning, supervised fine-tuning. You might even hear people talk about fine-tuning models. This is basically what it is. You give it some input, you give it some output, and you try to introduce some kind of behavior change. That's the purpose of this process. Yeah, Lucas, please.
Yeah, sorry, one more question. I wanted to know like how the reward system works. So where does the reward get stored, or like how does this work?
So I'll get to that part next, because before we even get to the reward and the dog training and everything, this is the first thing that we usually go through. We usually try to just boil it down, get it down to something that's a little bit more reasonable. Now that we've got that process, we're going to introduce the idea of a preference model, which is where we start rewarding things. As for the idea of kind of storing things and so on, that's actually by changing the weights. So we don't necessarily store all of the results that the model has given us. What we basically do is we run the model through some kind of simulation, some kind of environment. We kind of train it in a much smaller context. That's where this happens. So there isn't really like necessarily a data store for everything. It's really just the weights that are being changed. So in the fine-tuning process, we are also changing the weights, but I don't want you to think of switching it like a knob all the way from complete hot to complete cold. We're kind of just turning it a little bit. So people like to give the analogy of you're taking a shower and you turn the shower to some kind of setting and it's just way too cold. A pre-trained model would probably just turn the model all the way too hot. And then you would be scalding, and then the pre-trained model will say, oh, my mistake, let's go all the way back to cold. Let's go all the way back to hot. A fine-tuned model will say, oh, let's kind of wiggle in between, wiggle in between, wiggle in between. Cool, now you've got the perfect temperature. So that's really the purpose of these trainings. Dima, you had your hand up, or Dima Room, what's up?
Yeah. So can you hear me?
Mm-hmm.
Yeah, okay, so just a quick question about preference models, like this, it sounds like this is step by step. And when I used ChatGPT, I know that's another model. One thing they do sometimes is they give you two answers and they ask you which one do you prefer. So are we obviously you don't know the specifics about OpenAI, but would that be them training their next preference model with our?
It's a great question. I love that you brought up that analogy because I was going to use that in a little bit. But yes, if you have used those kinds at Anthropic, we don't do that. We don't train. We don't actually do anything with your prompt data. We don't train our models based on your user data or prompt data or so on. OpenAI may or may not. So if you have seen things in ChatGPT where it said, pick which one you like better, one or two, that is actually you performing. That's you being the preference model. That's not necessarily training the preference model. That's you actually doing the work of the preference model. What you are doing is you are putting the model in a certain scenario by asking it a question. You are actually doing what's called reinforcement learning from human feedback, or RLHF. You are putting the model in some kind of scenario. What does that mean? You're having a chat with it. What's the scenario? I don't know, whatever your chat happens to be about. When you give the model the answer, it's A or it's B, you are acting as the preference model. But what you're basically doing is reinforcement learning from human feedback. You're not doing it automatically, you're doing it manually. And that is a process that many models go through, and that's why companies like Scale AI and so on, or Amazon Mechanical Turk have thousands or tens of thousands or hundreds of thousands of humans doing this kind of work. What you're doing is essentially the same thing as them, but OpenAI lets you do it in a much more friendly way. But that is basically it. Yeah. Any other questions, y'all? A preference model is a model that's trained to evaluate the quality of outputs. So instead of figuring out the next token, the model figures out, is this helpful? Is this safe? Is this grounded in truth? Is this correct? Is this incorrect? We can make lots of different preference models. And in this case, we might have a preference model that's just focused on, was your answer helpful? We might have a preference model that is strictly focused on, is this safe? That's actually what constitutional AI is built around. One model that just figures out, is this safe? Is this not safe? And then we're going to train the model on what safety is and what it should avoid doing. The preference model consists of pairs of behavior and a label for which one is better. It basically looks something like this. You give it a training data, who are you? You give it a good answer and a bad answer. So who are you? I'm Claude, nice to meet you. Or bad answer, I'm your worst nightmare. We then go ahead and give it a score. If you ask, who are you? And you say, I'm your worst nightmare, we're going to give that a negative 2.7. The numbers themselves are relative. Usually that's between -1 and 1. But we basically put the model through lots and lots of iterations of getting scores from the preference model. And based on what the preference model outputs, we can adjust the weights to get answers that are more preferred. This can be done programmatically, or this can be done with humans. And that's pick the option that is better, A, B, or C. With reinforcement learning, once we've trained the trainer, once we've trained Elie Schoppik, the dog trainer, it's time to train the dog. In reinforcement learning, the model is given prompts and its completions are rewarded or punished. So in the previous step, in the supervised learning, we gave it the question and we gave it the answer. And we told it to just kind of pattern match the answer. Here, we're letting the guardrails off. Here, we're saying, I'm going to go ahead and just let you do what you can. Let you answer this question, let you give your input, let you determine if this is helpful or harmful or so on. And then based on the scenario that I put you in, that could be up to whatever machine learning engineer wants to make in reinforcement learning, we're going to take the preference model and we're just going to score how you did. And we're going to nudge you in a direction that's good, and we're going to push you away from a direction that's bad. And we're going to do this again and again and again. So for example, in supervised learning, we say, here is a good answer to the question. What is your name? My name is Claude. Great. In reinforcement learning, we're just going to say something like, what's your name? And if you say something like, I am a taco, we're going to punish that. If you say something like, my name is Claude, we're going to reward that. And then we're going to keep doing this again and again and again in different simulated environments. This idea of reinforcement learning is where we're actually seeing quite a few breakthroughs. So if you were to go look at OpenAI's latest model, O1, and you look about, how did they figure out this idea of being able to think through things step by step and so on, you'll see the word reinforcement learning quite a bit. So that model, that particular model, was put in a lot of environments where it had to figure out a different way or a slower but more methodical way of thinking. So that's where you can hear that term reinforcement learning quite a bit. Reinforcement learning is often done by a machine or programmatically. You might hear of reinforcement learning for how we taught machines to win at chess or win at Go and so on. Reinforcement learning from human feedback, that's where you as the human are the preference model. That's where you as the human pick option A or option B. With reinforcement learning just on its own, we train a different model, the preference model, to say yes, say no, nudge it in the right direction. So that's a lot on how these things are built. Again, I don't need you to memorize all these terms. I don't want you to be a expert on neural networks themselves, but I want you to just walk away with this idea of what is the thing that I'm using, whether it's Claude or GPT or whatever it may be. It's just a glorified text completer. It just figures out what the next piece of text or entire piece of text or word or so on is in a series of words. We break apart those words into tokens so that we can do a lot of math on them. And the math that we do is from the architecture that we determined. Who picks the architecture? A team of machine learning engineers or researchers at a artificial intelligence lab or company. Different LLMs have different architectures. Some showcase theirs and talk more about it, others a little more hush-hush. Once we figure out our architecture, we're going to use NVIDIA GPUs. We're going to spend this much money. We're going to buy this many GPUs. We then figure out where our data is going to come from. And then we're going to go ahead and spend a bunch of time training this thing to figure out patterns in language. We're not just going to figure out if it can take text and figure out the next word. We're going to figure out if it can start to develop an intuition for language, if it can start to understand attention mechanisms and context, and the architecture that we have is accurate. We're then going to get this giant text completer. We're going to fine tune it. We're going to fine tune it by giving it good questions and answers so it learns some good behavior. And then we're going to bring in humans and we're going to bring in other models into the mix. That's the idea of reinforcement learning in this process. So a lot of terminology, but I want to make sure you kind of have an idea of how that works. Any questions before we kind of shift gears to our next step? Again, this second part is going to be a little bit more in just the, how we work with Claude, how we prompt Claude. There are also quite some more slides I'm happy to share at the end, but I think things you might have seen before, things I want to go over at a high level, and if you have questions, ask away as we go through. So we're going to shift gears, talk a little bit about prompting with Claude, because this is not something that you should try to do from scratch. This is something that we have tools to kind of help you with and things that will just get better over time. So I'm going to show you a tool that we have if you have not seen it yet. If you have, great, I'll go over this relatively quickly, and that is the prompt generator or meta prompter. Again, what's a prompt? It's information you pass to a large language model to elicit a response. Just like what we talked about, the information you put in, that prompt you put in, gets turned into tokens, goes through a bunch of math, figure out the next token, continue. This includes lots of information, context for your task, data, conversation history, instructions, examples, and so on. In fact, your prompts may start to look something like this. And this is the very colorful slide that you may look at and squint a little bit and say, oh my God, how am I ever going to remember all these pieces? And the answer is you're not. Best practices with prompt engineering change pretty frequently. As models get better, as models get more capable, as we start working with smaller models and need to augment them with prompts, as we think more about safety considerations. So many times when you are building a prompt, it's really difficult to keep in mind all these pieces. And that's why we developed a tool to make your life much easier. And that is called the meta prompter. If you go to the Anthropic console and you go to generate a prompt, you can go ahead and give this some kind of particular task, like write me an email. Draft an email responding to a customer complaint and offer a resolution. Let's imagine that's my scenario. Or better yet, let's pick a different one. We're going to go ahead and actually generate a prompt where I, pick for me some exercises I can do that will strengthen my entire body. So let's go ahead and get this to generate something interesting for me. What we're going to get here is actually a prompt that is written by an LLM. That's why we call this meta prompting. if you look at this, you're going to see right here, it follows a lot of good practices. We set the stage with what we want. We have some dynamic information about the user themselves. This is where we might ask, put in your age, your fitness level, injuries, equipment, and so on. And then we're going to also have some guidelines. Then we're going to present recommendations. We're going to use these XML tags for how we handle things. We're going to tell it how to think. And then we're going to tell it to present your response, including everything. So instead of you having to come up with the prompt from scratch, you can go ahead and just start working off of this on its own. And if you want to go ahead and play around and test this prompt, you might be thinking, oh man, I have to like fill in the blank for the user info and so on. Nope, you can actually just have Claude generate some dummy data for you. So when you start thinking about what your prompt is going to be, for whatever application that you have, for whatever you want this AI to be like, you can go ahead and just start building for yourself a place to start playing around. And here's what I get back. Here are the things that we should think about. I can take a look here at the exercise plan that I get back. This starts to get, pretty long-winded at a certain point. So I can go ahead and I can start thinking about modifications that I might want to make. So you're a fitness expert. Your goal is to set exercises that provide a comprehensive full body workout for the user's information. Please keep your response as short as possible. I can go ahead and change other things here. Aim for a balanced workout that could be completed in, let's say 60 minutes or no less than 60 minutes. Now I can go ahead and see, based on this prompt, what my result looks like. And you can see here, I kind of get this V1 and V2. If you're familiar with Git or version control, it's very valuable over time to keep track of the prompts that you make so that you can go and iterate on them. In fact, something we've seen people do is actually figure out 3 or 4 or 5 different prompts and then give them all back to Claude and say, optimize these or figure out one prompt based on all these different ones that I have. So there's so much iteration that can go in this process. This is not stuff you want to do from scratch. So highly recommend you use tools like the prompt generator to figure out what your prompt is. And the best part is you can just grab the code for it after. So instead of worrying about copying and pasting all this information and so on, you can go ahead if you're using Python or TypeScript, or I think that's probably just going to be the ones that you're using. I don't think you're doing much on the AWS or Google Cloud ecosystem, but you want this code? Great, you got it right here. So when in doubt, you can go ahead and handle these particular pieces and get the code that way. Do not be afraid to use AI to help you in your coding journey, as I'm sure many of you know. So leverage the tools that you have to get things up and running as quick as possible. You all learned about MVPs pretty recently, so it's really nice to have these kind of tools to just get off the ground and build stuff. The meta prompter maps a short task to a prompt for Claude. We've given it a prompt that captures many best practices. You get start from here and you iterate as you go on. Console.anthropic.com to play around. The prompt structure that you get follows a pretty good pattern. And in general, this is what we recommend for the best accuracy. Start with a role in a task, any dynamic content, or in the case of retrieval that you're doing, or content that is being generated for you, or embedding similarity searches that you have that you pull in and results from there. That goes here in this section. Some detailed instructions, some examples, and some critical instructions that you want to make sure it really pays attention to. You're going to see in quite a few of these prompts that we use XML tags. XML, again, think of it like HTML, but you have to pick the name of the tag. If you have a relatively short prompt, XML tags are not going to do much for you. But as your prompts get longer and longer and longer, it can be really helpful to break them up into some particular kind of structure. And to give your prompts some kind of structure associated with them, XML tags are really nice. Claude is also trained on quite a bit of the internet, so it's familiar with this idea of tags and semantic meaning. So disorganized prompts are hard for Claude or any human to understand. Use XML tags to organize. Just like with titles and headers and indentation for humans to better understand things, XML tags will help you understand the prompt structure. Like we mentioned, Claude's been specifically trained on XML tags as well as quite a few other ones. So in general, you will see a lot of these XML tags floating around. If you need to programmatically pull out what is inside of the XML tag, that is a little bit of string manipulation, a regular expression, again, something that Claude can also write for you very easily. So don't be too intimidated by responses that have these tags and having to pull some text out of those tags. We mentioned quite a bit when prompting to provide examples. This is one of the most effective ways to get what you want out of your prompt. When we talk about the examples themselves, start with a couple. You don't need, 60, 80, 100, 1,000 examples by any means, but just good to have at least 3 to 5. Think a lot about the diversity of your examples. So if your examples are all relatively the same thing, you're not going to move the needle much. So think a lot about the examples that you want. And when in doubt, it's always better to show an LLM what you're trying to get, as opposed to trying to explain to an LLM what it should be giving you. So what I mean by that is, if you have a particular example of what the question might be and what the answer might look like, that's a good example. Instead of trying to tell the LLM, I'd like your example to include the following, or I'd like your answer to include the following, blah, 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 just show me. A lot of this is really that pattern matching, pattern recognition part that can be really valuable to get more accurate responses. The last thing that you can do that you can't do with all kinds of large language models is pre-fill the response. And what pre-filling the response basically means is programmatically, you can put words into Claude's mouth. So what I mean by that is, you can actually tell Claude something like, I want you to start your response with, excellent question, here is what I recommend. And what this basically does is it starts putting words in Claude's mouth to figure out the next token a little bit more effectively. You don't get a huge bang for your buck by pre-filling a response with something like, excellent question, here's what I recommend. You get a lot of value from pre-filling the response when you want to have greater control over the format of your response. So if you tell Claude, I want you to respond with JSON and I want it to look exactly like this. I want you to respond with XML, it should look exactly like this. I want your answer to look exactly like this. You can give it a bunch of examples, but you can actually start to give it the beginning of the response. With JSON, that could be an open curly brace. With a particular tag, that could be the start of that. This is very helpful for trying to steer the behavior a bit. This is a very, very common way to kind of get closer to the answer that you want. Yeah, demo room, what's up?
I'm sorry, now I have just one question. So is it possible to, for example, render the React component on the chat UI and then just like render it on the front end? Is this do this too, if you Claude Response give an availability actually to make a generative UI?
Yeah, absolutely. If you wanted to do something like, generate a particular UI for me, generate a React component that does XYZ, here's an example of what I'd like that component to look like. Here's what the component should do. And if you pre-fill the response with something like, whatever you want your component to be called, like, user info with a, prop of first name of, Elie or whatever that may be, you can absolutely kind of pre-fill the response that way. And in this case, it's not going to be very helpful, but in the case of, you want to make sure that the component is named correctly every time. You want to make sure that the component follows a certain convention every time, or maybe you want to start with your type definitions if you're using TypeScript. Absolutely. That's definitely where this can be helpful. You can then, feed that to a front end and do whatever you want with it, or Ajax, or however you're, consuming the API. Yeah, Lucas, please.
Is it, if you use something like this and you put the temperature higher, is there a danger that it won't follow the system prompt?
It's a great question. When you change the temperature, that's usually where you don't have too many issues with system prompts being followed. You're just going to get responses that are more varied, whether that's more creative or so on, whatever you want to call it. That's really just what temperature is going to do for you. If you're dealing with a particular kind of use case where something like classification, right? The answer is going to be valid, invalid, spam, not spam. I know clearly what this classification is. That's where you want your temperature to be really, really low, because you just want to make sure you're really picking something. When you're doing more creative writing, when you're generating assets where you want there to be a little bit more differentiation, that's where you can adjust the temperature. But many times, even especially with things like coding, wouldn't really jack up the temperature much. You're not going to get kind of more ideal outputs, especially when if the probability of something that is wrong is picked and it's a syntax error, for example, you're really not getting a lot of wins from, the different pieces of temperature. So temperature is not going to get you to a point where it's like, I would redesign this entire database schema in a completely different way. It just might pick some things that might be less likely to be correct. So wouldn't get too many benefits from there. With things like system prompts not being followed, system prompts not being followed gets a little bit more likely when you have a very, 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 very long conversation. So if you happen to have a, context window of 200,000 tokens or a million tokens or so on in the case of other large language models, when you get really late in that conversation or lots of tokens already, it's sometimes hard to adhere to the system prompt. So that's where there's some challenges with these models. Any other questions here? All right. Again, What's the TLDR, the too long, don't read about this? If you want to look at the underlying structure, if you want to look at the prompt that generates the prompts, you're more than welcome to look at that. That's completely open source. Again, this solves the blank page issue. It is not guaranteed to be anything perfect, but it's a really good place to start. So definitely recommend looking at that as you get up and running. Getting started with the SDK. Again, you've actually all seen how to do this in different examples. So if you're using Python or you're using Jupyter Notebooks, install Anthropic. Or if you don't want to use pip and you want to use something like Conda, which is great because pip does have its set of issues on its own, you can go ahead and do that. Make sure you have an API key, import Anthropic, and go ahead and use it. The reason why I'm not covering too much of all the underlying work in the SDK is because it's actually relatively easy to get up and running with. Compared to other APIs in general, large language model APIs are not incredibly sophisticated with hundreds of endpoints and so on. The other thing that's really nice that you may or may not know is at the docs for Anthropic, this Ask AI feature is a really good way to get things generated for you. Don't just think of this as, this is the thing I use to ask questions for the docs. You can ask this anything, and it will use the knowledge of everything at Anthropic that we have. So using the Python SDK, give me an example prompt with a tool for fetching a user by their ID. Now, what I'm doing here is not actually asking the docs themselves for any particular reference. I'm just talking to this like a large language model. And here's where I can go ahead and just get that code. So, hey, I have questions on tool use. Okay, interesting. So yeah, let's see, we're getting a bunch of extra stuff here. Yep, this can be helpful for playing around with things, but actually, I want to use Opus instead and just give me the first request to the LLM and not the remaining requests. You can have a full-on conversation with this. You can also see the source for where this comes from. You can ask this to explain stuff to you. So this is just like using Claude.ai or any other tool. But what's nice about this is this leverages all of the up-to-date courses, up-to-date documentation, and so on that we have. And this can go ahead and work with us. So we can go ahead and get the data we want. We can have back and forth conversations with this. And we can go ahead and head over to where the sources are for this. So in terms of just kind of getting up and running with the code, there's not that much, and you can really lean on a lot of the existing tools, whether it's asking our documentation or just going to Claude AI or other places on the internet to find what you're looking for. So getting up and running, I know you've seen that kind of quite a bit, so I don't want to hammer that home too much. What I do want to talk about, though, is something called tool use. You might have heard this term, you might not have heard this term, tool use or function calling. Tool use or function calling is how we get our LLM to tell us about things that it doesn't originally know about. So what I mean by that is, if you want a particular way to search the web for something, or you want to go to a database and find a user by their ID, if you ask Claude that right now, Claude's going to say, I have no idea what you're talking about. What database, what users table, what ID column, no clue. Tool use is a way to, in your prompt, notify Claude that if there is a prompt coming in that asks about something that it doesn't know about, take a look at those tools and see if they might be on the right track. Claude or any kind of large language model does not execute the tool. Claude is not going to execute a function. Claude's not going to go to the database. All that Claude is going to tell you is something like, hey, it looks like a user with an ID of 22 is trying to go and fetch their information. You, developer, do what you want with that. And you as the developer can make a database call, go to a cache, not do anything. That's totally up to you. So for example, when you start setting up your model, you give it a list of tools. Maybe I have one called get score, which gets the score of a baseball game. I have another called get song, which gets the most popular song. And when the user asks a question, instead of Claude saying something like, I don't know, or potentially hallucinating and saying something like 73, it's going to do a pretty good job at saying, I don't know in most cases. What it's going to do first is say, do I have any tools that might be on the right track? I don't know if this is a baseball game. It might be, but here's the team and here's the date. So you, developer, go and do what you want with that. The developer can then instruct Claude to take the score of a game or ignore it or whatever it may be. So all that tool use is basically kind of like a funnel or a pipe that extends the functionality of Claude. For example, you might ask something like your chatbot, look up my ID of 74. Or do you have any sneakers left that are XYZ model? By default, Claude's going to say, I have no idea what you're talking about. But if you give Claude a tool, it will say, oh, it seems like you're trying to use this tool. That will then go back and the developer can then go ahead and do what needs to be done. Go to a database, an API, an email API, whatever it may be. You then take those results and you give it back to Claude. And Claude can then say, oh, you have the user ID of 74, or whatever that may be. Or yes, we have sneakers left. We have 3 left. Go buy them now. Give you a little visualization of that. An application or a user might ask, how many shares of this company can I buy? The model says, I don't know what the current price is, but it looks like I have a tool here. The developer then gets that data, sends it back to Claude, and then Claude can say, here's what you got. I'll do a little bit of math for you. Here's what the current price is. So when you're dealing with any kind of functionality that Claude does not have out of the box, any kind of tool or function itself, this is where tool use comes into play. You can have hundreds and hundreds of tools with Claude, and here's what a tool looks like. Yeah, you give it a name, you give it a description. This is very important, the name and the description. That's how Claude actually figures out which tool you are trying to use. So when you talk about the weather, it's going to say, oh, I got a tool called Get Weather. That seems like you're probably on the right track. If you have used JSON schema before, it's a very common method for validating or typing. We follow that particular pattern. This is also how many other providers do the same thing. So that's essentially what we're doing here. Again, you can look at the docs for tools or tool use itself. If you've ever heard of the term agents or agentic workflow, agents themselves are basically just powered by lots and lots and lots and lots of tools. They just use tools independently. So that's why this idea of tool use, very important at a high level to understand. Question here. Yeah, Dima, go for it.
Yes, hi. With the tool use, can it actually run a function? When you say pass the request back to the developer, so it still has to be done by a human.
Oh, yeah. So in this case, human is in like the developer of this application. So you in your Python program would do something like take in some user input. You would get the result of that user input. In that result, Claude will tell you something like, looks like you're trying to call this tool. You then, with a little bit more Python code, will go ahead and have some conditional logic like, if it is the name of this tool, go and execute this function, go and make this API or database call or so on. So you as the developer or the application developer, you're responsible for actually calling the function. Claude is just responsible for taking some kind of input and saying, I think you want that one, or I don't know what the answer is, or you don't even need to use a tool, I know the answer. So think of Claude as just kind of the fork in the road.
But it can be pre-programmed.
Yes, yeah, absolutely. Yep, absolutely. Lucas, what's up?
Do the tools have to get sent with every request you're doing all the time? And is there maybe also a way of storing the tools in our own vector database?
So you wouldn't necessarily want to store the tools themselves in a vector database. The tools themselves are basically just a massive JSON blob or a whole bunch of JSON. There is something called prompt caching, which you can use that makes life much easier. So instead of sending the tools every time and re-tokenizing and generating tokens for the same tool over and over and over again, because just like your messages, you have to send them in the entire response every single time or prompt every time, you can leverage prompt caching, which basically will take all your tools at once, cache them, and then in all subsequent requests, not regenerate all the tokens again, just use that cache. So I would look at prompt caching to solve that problem.
Perfect, thank you.
Yeah, absolutely. Better to have lots of separate tools for separate operations. So in general, don't have one tool to try to do it all. And in general, be really, really, really clear about what the tool is that you're using. If you have tools that have duplicate or similar functionality, Claude's going to get a bit confused. So coming from object orientation, it's kind of like the single responsibility principle. You got one thing, do that one thing well, one responsibility. Each tool follow that similar kind of convention. So one tool should just do one thing really, really well. If you're doing some kind of CRUD action, you might have one tool for creating a user, one tool for updating a user. You wouldn't really have a tool for do stuff with users. So keep things, self-contained with the names of your tools. Again, for examples for how to do this and so on, head to the docs and just ask it for an example of how would I go ahead and fetch a user from the database. In fact, in this example here, we saw here's what it kind of looks like. You give it a particular tool, get a user, you pass that along, and if the message content type is tool use, then go ahead and continue the conversation. And in the context of this conversation, you can go ahead and here make a database call. You can then go ahead and take that data and send it back. So the idea of sending it back, this is where you would make the database call and send it back. If you wanted, you can keep building off of this. You can say, use the request module, work with Postgres, give me an example with a, SDK with Vercel or so on. You can have a conversation and get that generated for you and start playing. So I really want to just make sure you kind of lean on that tool. I got a beep for a hand up. I just want to make sure I don't miss anything. Any other questions here? All right.
Because, hi, I did look at tools on your website and it didn't actually have that much information. So would you recommend using the chat function to help to learn how to use them better?
The chat function is a great start. If you take a look at tool use itself, definitely, send me a message and let me know where the feedback is not great on that, because we can always update these docs at a high level. But here's what a tool looks like. When you go ahead and use that tool, you got a little bit more tools and so on.
Through reading through there, didn't see any clear example of using it at the kind of level that you're talking about.
So here's kind of an example that I would show in Python of we have a tool for getting the weather. And this is what it looks like. Here's the response that we get. This is the actual response that we get here. It's going to say something like, I need to call a weather function and the user wants SF, yada, yada, yada. After you get this response, you would then need to execute some kind of function that you have. You then need to take that response and give it back to Claude. So you would include the tools that you had previously, include the messages that you had previously, and then in the final response, here's where you can include the data that you get. So definitely lean on the chat AI as well to kind of help you in that process. But that's kind of the flow of how tool use works. We also do have an entire course on tool use itself that I definitely recommend looking into. And that's just from our website or Anthropic/courses. There's an entire course on tool use that really dives into that. So good place to start.
Thank you.
Absolutely. All right, last couple pieces. You've all seen kind of high-level architecture for RAG. So RAG is the idea of retrieving information that Claude does not know about. This allows us to remain grounded in the truth and so on. What is the idea of RAG? Some kind of question comes in. Claude doesn't know the answer, so it goes and takes that query, finds similar searches, and returns an answer based on similarity searches. I know Dima talked about this way back when, so you've got a pretty good idea of what the RAG architecture looks like. So I'll kind of leave you with these slides if you want to lean on and kind of see some examples. But where RAG gets a bit more interesting, the part that I kind of want to get to here, is the state of RAG currently. As more optimizations come out, RAG is going to change drastically. So RAG is something that in 3 months and 6 months and 12 months is going to look very different than what it did right now. I spoke quite a bit about prompt caching, and quite a bit, not too much. I'm sorry, it's a little bit of a misnomer, but I spoke a little bit about the idea of prompt caching, where you have a very long conversation. Instead of regenerating the tokens every time for that conversation, you just cache it. What that means is if the data that you need to retrieve is not tremendously massive, as the context windows get larger, as we have 1 million, 2 million size context windows, you can actually put a lot of your data that you would normally have to chunk and vectorize in your prompt itself and cache it. So as context window sizes get better, there may be many use cases where you don't even need to go the embeddings route and so on, and you can just have all your data in your prompt and retrieve it much faster and much more accurately. So larger context windows, again, it's not going to solve every single problem, but if we can get to context windows with 5 million, 10 million, and so on tokens, a lot of these use cases for RAG are going to go down quite a bit. We're using vector databases very commonly, but there's actually other kinds of data structures that have shown to be potentially far more effective than the traditional embedding models. So knowledge graphs are another mechanism if you want to look into that. There are lots of different optimizations for RAG as we go through. And again, I'll leave you with these slides. It's a really nice piece of research that we put out on contextual retrieval, which is another way of chunking and querying and so on. If you want to kind of be on the cusp of what you do with RAG. And then again, embedding models that we have change constantly. They're embedding models from OpenAI and from Voyage and from Google, and they're just getting better and better and better and better. So the way that we think about RAG is going to change quite a bit. How big the chunks are, how we think about ranking those chunks. So what I want to tell you about this process is things change very constantly. RAG is one of the things that changes even more, faster and faster. If you're interested in testing the effectiveness of your RAG, there are lots of frameworks around that. RAG or RAG as an evaluation. It's a really nice place there. Dima, go for it.
Yeah, I have a question. As you like, we discussed today on a workshop about versions of the libraries that were used to make our solution stable. What are advices actually to make embedding pipelines stable at this case?
Oh, that's an excellent question. It's really hard because you have to make the trade-off of if you're going to use an existing version, an existing technology, then you have to either lean on to some provider that allows for backwards compatibility or iterating on the next version relatively quickly. That is generally one of the biggest challenges in this space, which is, if you're, especially with providers like LangChain and Llama Index and so on, they just change so constantly. So you have to keep just iterating over and over and over and over again. In this ecosystem, it's a trade-off. In this ecosystem, there's no one best. If you stick with this library, you will be fine forever type of thing. I think the most important thing right now is don't over-engineer stuff. Give yourself room for flexibility if it needs to be down the line and so on, but do not think about having the most highly optimized or fastest possible system and so on, especially for the MVPs that you have. So stay grounded with it. But excellent question. I wish I had a better answer. Last little piece I want to talk about is fine-tuning. Fine-tuning is not something that you can do for standard applications with Claude. You have to be on the AWS infrastructure for fine-tuning. Fine-tuning is exactly what we spoke about before. It's where you give your large language model a bunch of good inputs and a bunch of good outputs, and you introduce behavior change. What that basically requires is a lot of data, some model, and a bunch of hardware and money. Fine-tuning produces a custom model, which can be great until new models come out and you have to do this all over again. So it can be a very expensive process. You want to be really, really careful when you do it. You will not be doing fine-tuning for the projects that you work on, but I just want you to be aware because it is a pretty interesting part of this ecosystem. Or if you're at a company where they're thinking about fine-tuning and so on, it's a permanent decision. There's no kind of undoing the fine-tuning. Fine-tuning is great when you need to introduce behavior change. Following a particular tone, teaching it a new skill, like make sure to always call that tool or make sure to always classify this in a certain way. But if you want to try to teach the model something and then hope it learns new things adjacent to that or expects it to remember tasks in a different way, you're not going to get very far. So I'll kind of leave you with this little note on fine-tuning because it's a helpful place to start. So small little bit on fine-tuning. You're not going to be doing it too much for your own individual projects, but it is the same kind of fine-tuning or supervised learning that we talked about a little bit earlier. You can do this at any point with your models. Open weights models like Llama and Mistral and so on are more commonly fine-tuned in lots of different use cases. You can fine-tune Claude models on AWS's infrastructure, but not what you can do kind of out of the box right now. So I just want to make you aware of that kind of idea there. Again, fine-tuning seems really exciting, but in general, make sure you are prepared to do it. Do you have the right data set? Do you have a high quality data set? Do you have ways to evaluate success? And have you tried prompt engineering? So anytime your boss comes to you and says, handle the evals or handle the prompt engineering and so on, do that first before you get to fine tuning. I know we're brushing up on time. I know this last little bit was relatively quick, but again, I just want to thank you all so much for kind of sticking with it. And this was a pretty long session for those of you that are going to be in London for this hackathon. Super excited to get a chance to meet you and chat about any of these pieces. So just want to see if there are any last lingering questions before we duck out here, but hope to see many of you very soon.
Elie, thank you for this workshop. I appreciate that. Guys, last questions. Some last ideas or I don't know. I have one stupid question. Actually, have an answer on that.
No, please.
This is more practical side. We are all here for actually making hackathon happen, and all of our teams have their paths which everyone trying to solve. And maybe I'm wrong now, but as I understand, the most useful pipeline for now is build some kind of realization of RAG, and at which we make, for example, we successfully all make an MVP version of our projects, their work, at which step we should think move from RAG to train the model? I mean, this question is related to your last topic for the presentation.
Yeah.
When we start to think about that, what are stable points or key things should be when we should start thinking about that?
Totally. So the most important thing to remember is, and there are tools like, AWS that offer this idea of continued pre-training where you can actually put in a bunch of new data and try to get the model to learn it. So you don't need something like RAG, but fine tuning is on its own not going to replace the need for something like RAG. Think of fine tuning as behavior change. I can change the way that you act, but I can't fundamentally change what you know or who you are. I can get you to talk a little bit this way. I can get you to follow my instructions a little bit more this way, but I can't teach you brand new things and expect you to remember them. So think of that trade-off. If there's external data, external knowledge, things that Claude does not know about, fine-tuning is going to be really, really hard to get to be reliable or really expensive and not 100% successful to teach it brand new things. So the trade-off really becomes, do I want to just steer this model in a certain direction, kind of like what we did in the fine-tuning process when we train these models? Or is there just a bunch of data this model doesn't know about that I need to make it aware of? And if it's that second category, RAG is just definitely what you're going to be doing. So that's why you'll see in many cases, regardless of whether you're using RAG or not, fine-tuning happens only when you're not getting the kind of consistent format of responses that you want. So tools are not being called in a certain way. That's definitely where you'll see that in a little more action.
I appreciate that. Thank you. It was amazing. Thank you.
Awesome. Cool. Thank you all so much. Really appreciate everyone and hope to see many of you soon. Take care, everyone. Have a great day.